Welcome to the first video topic for Physics 102. This video covers the difference between average and instantaneous acceleration, as well as discusses the graphical interpretations of acceleration. Now in class we discussed the idea of average and instantaneous velocity. Now we're still going to restrict ourselves to so-called one dimension. We're still only going to move in one way, either back and forth or left and right, just one at a time. And we're just going to label the direction that we are going to move in. We're going to go ahead and label it the quantity x. Now, in one dimension, the average velocity is defined, so v with a little bar over it to distinguish it as average, and we're moving the x direction, so let's put a little subscript. That subscript will be important later, is defined to be the change in the position over the change in time. Now this is an equation that's on your equation sheet, so you should be pretty familiar with it. To write this out a little bit more, what do we mean by change in position? We mean we take our final position, whatever that may be, and subtract the position we started at. And we divide that by how long did it take us to go this far. So our final time minus our initial time. And this is the quantity of average velocity in one dimension. Now in class, we also discussed the idea of a position versus time graph, such as the one that you see in the lower left here. Where, how do you make one of these? Well, you go along and every instant you go and you figure out where you are along this x-axis and you mark it down and you make yourself a little plot. Now if we look at the expression of average velocity here, we can see that it is a rise over a run, or a slope. So this is a slope, and the average velocity then between, say, these 2 points is the rise divided by the run, or just the slope of this line here. Or if we wanted to consider the average velocity between these 2 points, we would connect them with a straight line, which has a rise and a run. And we'd be able to calculate the average velocity between these 2 points as just the slope of this line. Now, what if we were more interested in the velocity at, say, a particular instant? Like, what does your speedometer read? As in, what if we were interested in the velocity just here? What would a speedometer read there? Well, how could we go about it? Well, we discussed this a little bit in class 2. We could take the average velocity this way, or we could do it with 2 points that were a little bit closer, and keep moving these 2 points closer and closer and closer together until we got the slope at that particular point. And the slope at that particular point would be the instantaneous velocity. So this is what your speedometer would read at this particular moment in time, and we write it down in a similar sort of way. This is instantaneous velocity, still in the x direction, but since it's instantaneous, we don't put a little bar over it. And we indicate that we've done this procedure of take these 2 dots and move them closer and closer together with this lim standing for limit notation. We've taken the difference in time and we've made it as small as we like. Your speedometer actually works by taking a measurement 2 times very, very close together, and then we do the slope, the rise or the change in position over the run or the change in time. Now let's move on to our new quantity, acceleration. Acceleration is to velocity as velocity is to position. So what do I mean by that? Acceleration is the change in velocity divided by the change in time, just as velocity is the change in position divided by the change in time. And just like we can make a position as a function of time graph, we can make a velocity as a function of time graph, where the horizontal axis is still time, here measured in seconds, just like on the position graph, but your vertical axis is instead not position, but instead the velocity at each instant. So what you're looking at here is you're going to be plotting what does your speedometer show you at each instant in time. Now let's say I'm driving my car and I start at a stop So my velocity is 0. And I press on the gas, and so my velocity starts increasing, and I'm driving in the what I define to be the positive direction, so my velocity is positive. And then I drive along at some constant speed for a while, and then I have to apply the brakes rather suddenly, and I come back to a stop. So at this instant down here, I'm at a stop as well, because we can see that here my velocity is also 0. Whereas up here, we can see that my velocity does not change, and so this means I'm driving along at some constant speed, say 20 meters per second or something. Now acceleration is just defined as the change in velocity divided by the change in time. So we'll start, as we did with velocity, with average acceleration, where average acceleration, we use a little a for acceleration. This is an average, so we put a little bar over it. We're still just dealing with the x direction, so let's put our little subscript. It may seem silly now, but it will be important later. And this is going to be the change of our velocity in the x direction divided by the change in time. Now once again, we can see that this has the shape of a rise over a run. So once again, it's a little slope. So let's say we were looking at the acceleration of my car between these two moments in time, 0 here and this moment here. Well, if we wanted to find the average acceleration, then we would say, okay, I started, my initial velocity would be 0. My final velocity in this case, we know is 20. How long did it take? Well, my initial time is defined still to be 0. And my final time, I don't know, let's make this 5 seconds or so. Now make sure everything has units. And then my average velocity over this trip is going to be 20 over 5, or 4, and that's going to be meters per second squared. And that's going to be my average acceleration, average, so it gets a little bar, for this entire trip. And since it's a rise over a run, that's also going to be the slope of this line here. Okay, so it's just an analogy with position. Only I'm looking at a velocity as a function of time graph as opposed to a position as a function of time graph. And just like with velocity, I also have an instantaneous acceleration, where instantaneous acceleration means what's the acceleration, say, at this time, say at 8 seconds. What's the acceleration there? Well, this isn't a line, but we can imagine maybe doing a similar thing like we did with velocity, taking 2 points on either side, connecting them with a line, using this rise and this run to calculate an acceleration. But that's not going to be very good. We'll get a better estimate if we use 2 points that are a little closer. We'll get a better estimate of the acceleration at this point. And just like with velocity, we bring our 2 points closer and closer and closer together until they're as close as we care to go, and we use those to measure our acceleration. And that's our instantaneous acceleration, no bar over it. So that's just going to be, again, we'll use this limit notation. We're bringing our 2 times closer and closer together. So the delta t is getting closer and closer to 0. And we're measuring the change in the x velocity over the change in time. Now let's try putting everything together. We know that instantaneous velocity is the slope of a position versus time curve, which we can write the idea of a position versus time curve mathematically as x of t. And the instantaneous velocity is going to be the slope of that curve at any given point. Meanwhile, instantaneous acceleration is going to be the slope of a velocity versus time curve, which we write the idea of a velocity versus time curve mathematically as v of t. And the instantaneous acceleration is going to be the slope of that curve at some point. So here we have a position as a function of time in the green. So if we go and we look at this, the slope of this curve is positive. It's greater than 0. It's running upwards. So the velocity is going to be a positive number. And it's always the same number. This is a line. It has some slope, and the slope is constant. And so we're going to get some nice flat line for velocity. Now, let's repeat the process. We look at velocity. What is the slope of the velocity at this point? It's 0. It's flat. What is the slope of the velocity at any point? It's 0. It's always flat. So what's the acceleration in this case? It's 0. There is no acceleration. And so we end up with a 0 acceleration at all the different times. So this is the basic idea of velocity as the slope of position and acceleration as the slope of velocity. This concludes this topic on instantaneous versus average acceleration and graphical interpretations of acceleration.